trying to figure it out together, because this is my first time trying to do it. UAH is talking about joining quickly attendance, which would be so much easier for me and you. You just get a nice little QR code and it would make things so much easier. But until such time, we're going to be using Point Solutions. So Point Solutions app, attendance is open right now, and we'll go from there. There was a couple of questions via email and everything else. If you look on Canvas, you will notice that your first assignment due date is next Monday, I think is what it is. But there was a reading quiz on Achieve that didn't show up on Canvas. And that's because, frustratingly so, if I create an Achieve assignment that is ungraded, it will not show up on your calendar in Canvas. So there was a Chapter 21 reading assignment due yesterday on Achieve, but it is ungraded. It will not be counted for or against you in Canvas. That's why it didn't show up in Canvas. So if you read my announcement and you saw it and took it, great, that was to your benefit. If you didn't read my announcement, learn to read my announcements, but also it doesn't penalize you. Last class period, we left off with the discussion on how charge works, what charge is, how charges interact, the repulsive and attractive nature of charges. I mean, the whole shebang, right? And today what we are ready for is what is known as Coulomb's Law. And I love Coulomb's Law because it is, it's born out of 3 different observations that Coulomb himself made while he was trying to study this phenomenon that Benjamin Franklin had tried to quantify a couple decades earlier. So what Coulomb noticed is that there is a force between charges. I mean, that's why we say attractive or repulsive, right? And so what he noticed was that the force is directed along a line connecting the charges and is inversely proportional to their separation distance. Does that sound vaguely familiar to anything that we talked about in Phys 1? Gravity. Yes, gravity is a force that is along the line that connects two masses, and it's directed always towards each other, no matter how you orient those two masses. This is the same kind of phenomenon. The only difference with the electric Coulomb force is that when you draw a line connecting two different masses, that force, if it is attractive, meaning a positive and negative charge, is going to be directed towards one another along that line connecting those two charges. Or if it's two like charges, it's going to be directed along the line but away from one another. They're repelling one another. And then inversely proportional to the separation of their distance. That means as you get closer and closer together, as distance between charges decreases, magnitude of force increases. Just like gravity, right? As we move away from the Earth's gravitational pull weakens on us. As you separate charges, their repulsive or attractive force weakens. It's also proportional to the magnitude of the two charges, just like gravity. More mass means more gravitational attraction. More charge means more charge, attraction, or repulsion. So if I have 1 nanocoulomb of charge in one ball and another 1 nanocoulomb ball of charge, and then I up the charge in the second ball, then I would up the force between these two objects. And then the last is what we have already stated. Attractive is the force is attractive if the charges are oppositely signed, meaning positive and negative, and it's repulsive if they are the same sign. Now the convenient thing is Coulomb was able to take these 3 statements, and just like we had for gravity last semester, the 3 previous observations are combined into what is called Coulomb's Law, where the magnitude of the force is equal to some constant k, which you can see down there at the bottom, times Q1 times Q2, all divided by their distance of separation squared. Again, this is, at least in form, almost identical to gravitation. Gravitation, where you had GMM over R squared, now you've got KQQ over R squared. So K is going to be called Coulomb's constant, and it's equal to 8.9876 times 10 to the 9 Newton meters squared per Coulomb squared. And you think, okay, 10 to the 9, what would that be? A giganewton of force between two objects that are separated by 1 meter that both carry 1 Coulomb apiece. So an extremely high amount of force, which is why we only see small collections of charge in the universe. Because the force of the electric field is so strong, the electric force is so strong that such an imbalance of charge, the universe seeks to reorient itself and balance that charge very quickly. And so you don't see, if for example, that wall was positively charged and I was somehow negatively charged, it is unlikely that I'd feel a strong attraction to that wall, mostly because we can only build up microcoulombs of charge on me and the wall respectively, meaning that the force would be less than giganewtons, in fact, less than a newton. Now, the second form of Coulomb's law is actually the more complete form, and that is the vector form, where the question that I usually get is, why is that listed as F12? It's not F12. The way that you read that is the force of charged particle 1 on charged particle 2. So the force of charge 1 onto charge Q is equal to K times Q1, Q2 over R squared, where R12 is the distance between charge 1 and 2. Okay? So the force of charge 1 acting on charge 2 is equal to some constant K times the magnitude of their times their charges, divided by the distance squared between them, times R sub 1, 2 hat. Does anybody know what that little hat indicates? Henry? What? It's a unit vector. A unit vector is something that has magnitude 1. So that is magnitude 1. It has no additional units to it because you take the vector and divide it by its magnitude. So there are no units attached to it. So a unit vector has magnitude 1. So it doesn't change the scale of the vector, this KQ1, Q2 over R12 squared. It just tells you in which direction it's pointing. And guess what? It's pointing in the direction of R1 going to R2. Okay, that's exactly what we see here. Unless Q1 or Q2 is negative. If Q1 or Q2 is negative, well then a negative on a unit vector is going to flip its direction, in which case you'd see this pink being in opposite direction of R12, so the force would be back towards Q1, meaning it's attractive because the signs are opposite one another. Questions, comments, concerns? It's day 2 and we're already doing vectors? Yes. Yes, we are. If that makes you sad, then just go watch Despicable Me. No, that was just in one dimension. We're not talking about just left to right. We're talking about any which way these charges can be oriented in space. We'll do an example problem here in a second. Vector. Yes?
So this is for attendance, saying that I'm outside the range.
Really? I set it to a 45-meter radius. I appreciate that their units are in meters, by the way. I'll try it on Thursday without location based on, figure that out. Yeah. Yeah, your laptop may be connected to a Wi-Fi thing out there or something. I don't know. I don't know how location-based services on laptops work. I only know how they work on phones. All right? Again, I'm not going to kick you out of the class if you don't make attendance today. Today's a practice run. The Coulomb constant K is now defined, I say is now defined, meaning that when Coulomb discovered this, he didn't define it in terms of an additional constant. But we now know, physicists now know, I should say, that K is defined in terms of a more fundamental constant, epsilon naught, which is known as the permittivity of free space. That is, K is equal to 1 divided by 4 pi epsilon naught, where epsilon naught is 8.854 times 10 to the minus 12. You don't know what farads per meter is yet. We haven't gotten to that, but that's at least, if you look it up online, the unit's what it is. Farads are a measure of capacitance. So if you're an electrical engineer and you've worked with the capacitance, the farad is a measure of how much charge can be stored per volt. So we've got charge per volt per meter. So how much capacitance you have per amount of space. Not super important. The reason that I stick this in so early, normally I don't worry about it until the end of the semester, is because Achieve has homework problems that have you use epsilon naught, even though they don't introduce you to epsilon naught for like 3 more chapters. So I'm introducing it to you now, so that way when you see it in the homework, you know what epsilon naught is and how it relates to K. Okay. So, 2 objects initially experience an electrical force F if the distance between the objects is halved. So we go from 1 meter down to a half meter. By what factor does the force change? All right. So the correct answer is that the force would increase by a factor of 4. Because we are dividing by 1/2, but then we have to square it, right? It's 1/2 squared. So 1/2 squared is 1/4, but we're dividing by 1/4. You have to bring the denominator up to the numerator, and so we get an increase. When you bring things together, the force increases, and if the distance is halved, it's done so by a factor of 4. Any questions? Yes, right here. The square, that is in the definition of Coulomb's law, right? So it's r squared here, or it's r12 squared here. So by definition, as you take it, if you want to see it worked out, that would be a good exercise. You can't see my second screen, so that's fruitless. I've got the original force is equal to something, let's say, divided by 1 meter, right? But I want my second force to be, and that would be squared. Then I would have something divided by 0.5 meters squared, or that would be equal to 0.25 square meters here. And when I divide by 0.25, that's the same as multiplying by 4. So from Coulomb's law definition, that's where I got the square. Okay? Let's see. Full screen here. All right, let's try a problem then. In a hydrogen atom, the electron is separated from the proton by an average distance of half an angstrom, 5.3 times 10 to the minus 11 meters. Again, I told you you're going to want to be familiar with some of the smaller SI prefixes for this semester. They're going to start popping up a lot. So we could have also written this out as 53 picometers. It's probably how I would have written it out. Or you could have done it as 0.53. I know this isn't an SI prefix, but 0.53 angstrom. Calculate the magnitude of the electrostatic force of attraction exerted by the proton on the electron. So I'm going to call this Q1 and Q2. We're just asked about the magnitude here. So I'm just going to use that first of the two equations, not the vector form yet. But I've got K times the absolute value of Q1 times the absolute value of Q2, all divided by the distance, which this is R right here, the distance between them squared. But my question to you is, what is Q1 and what is Q2? Think back to what we just discussed on Thursday. Yeah. So what was just offered, he said 1.6 times 10 to the minus 19. The charge of a proton is equal to plus 1 elementary charge, or that's plus 1.602 times 10 to the minus 19 coulombs. And then the charge for an electron is minus the elementary charge, so minus 1.602 times 10 to the minus 19 coulombs. So I've got K is 8.988 times 10 to the 9. I've got everything in standard SI units because I'm using coulombs here and meters here. So I'm going to leave off my units because they should come out to be units of force, times the absolute value of plus 1.602 times 10 to the minus 19 coulombs times minus 1.602 times 10 to the minus 19 coulombs. Turns out that's not going to be of major concern, the positive and negative, because we've got these absolute values here, meaning that we're just concerned with the magnitude, divided by the distance between them squared, so 5.3 times 10 to the minus 11 meters squared. And I, in the midst of getting ready for class, forgot to pull up my solutions here. So if you get it before I find it, that's fine. To the negative 11. You can't see it up there because we need a new projector in here, but now maybe it pops up. It's separated by a tiny distance, an electron and a proton, not a large distance, right? 10 to the 11 meters. What would that be? That would be on the order of like the size of our solar system. So 10 to the minus 11 meters. This comes out to be 8.2 times 10 to the minus 8 newtons. And you say, well, that's a tiny amount of force. I mean, if I was to convert this to standard, or to an SI unit prefix, that would be equal to 82 nanonewtons. You say, well, that's a tiny amount of force. But if you remember anything from Phys 1, hopefully you remember that a tiny amount of force can still mean incredible amounts of acceleration. How? Why? What? Yeah, you're dividing by the mass, and the mass of a proton and an electron are extremely tiny, right? So 8.2 times 10 to the minus 8 newtons when you're acting on an electron that has a mass of like 9 times 10 to the minus 31 kilograms. Yeah, that's an insanely high amount of force. So here's a question. With that high of a force, it turns out that we're getting into too much stuff here. What we found out is that when you accelerate a charged particle, right, when you cause it to change directions or speed up or slow down, what we know from graduate electromagnetic theory 2, or just general principles about the universe, is that charged particles tend to radiate energy when they're accelerated. And so we have this electron that is constantly being accelerated inside of the atom, right? Which means it should be radiating off energy. So whatever angular momentum it's got to keep it in orbit, it's going to lose that, and it should crash into the proton. Right? right? The nucleus. So what gives? I mean, this was the key issue with our understanding of electromagnetic theory and classical mechanics between the 1880s and the 1920s. How do we rectify that? The electron doesn't crash into nuclei. It should crash into the nucleus. So how did physicists rectify that? It's not the strong force, but you're on the right track. You're in the right time period. Yeah, Andrew.
Electrons have certain orbital levels that they have to maintain, and the amount of energy required to go from the first to the nucleus.
Yes. So if you didn't hear what he said, his answer boils down to quantum mechanics, which I love because this is one of those rare cases. You know, scientists all the time are like, okay, we know this is a law of the universe, at least as far as we can understand it. And scientists all the time are like, but what if it doesn't work that way? And usually they're wrong. This was one of the times where Niels Bohr, he suggested, but what if sometimes the universe doesn't work like that? What if the electron can only be at certain energy levels? What if they are quantized, meaning quantum mechanics? And it was one of the weird, random, awesome cases where it turns out his what if was correct. That his, like, what if it doesn't work that way? Well, I wish when I said it doesn't work that way, it turned out that correct, and I had whole textbooks written about my discovery. But there you go. Quantum mechanics is also something that we have to be concerned about when we're talking about electromagnetic theory. If you're a chemistry major or take chemistry, this is what physical chemistry is all about. Okay. Let's up the ante a little bit. 3-point charges, each of magnitude 3 nanocoulombs, are at separate corners of a square of edge length 5 centimeters. So we're not talking about protons and electrons. We're actually talking about a pretty significant amount of charge here with nanocoulombs. They're separated along the square with 5 centimeters. 2-point charges at opposite corners are positive, and the third point charge is negative. Find the force by these point charges on a fourth charge. This problem could have been made so much easier if they said, oh, hey, by the way, you've got this configuration right here. I don't want to write, that's like a celestial, I want to see what that looks like. We're not going to be doing problems with, I don't know, I don't get that. I thought that was blue at first. We're going to go with blue. Okay. So let's get back down here. So what we've got is this, where we're going to call this Q4. And then we've got up here, we've got, actually I've got it drawn differently and I'm going to confuse myself. Let's do it this way. This is going to be Q4 in the top right. And then we've got a positive, all of these things got reset over Christmas. It's a wee bit frustrating. We've got a positive Q here and a positive Q here and a negative Q right here. So if you didn't get that from the long, many words in this problem, this is what they were trying to tell you, where you've got this length L. Oh, so frustrating. Let's see here. Where you've got this length L right here is the sides of this square. Find the force exerted by these point charges on Q4. So we want to know the force on this charge Q4 right here. And so I ask you, if I'm looking at Q4, it should have experienced a force from the other three charges present in this problem. Right? Because charge is attracted or repelled by any other charge in the universe. So, my question to you is, if I'm looking at Q4, with respect to this charge on the top left corner here, in what direction should, I drew that in the wrong color here. Let's do this, because it's a positive charge. So I've got Q4 right here. So if I'm looking at this configuration where you've got positive, 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 and only one lone negative here, in what direction should the force on Q4 be from the top left charge? Left, right, up, down, out of the screen, into the screen. What? Not the net force. Right here. What's? Well, it is drawn towards the negative Q, and so if I'm just looking at the force from this guy on this guy, yes, there's going to be a force down this way. Let's call this F2, where maybe this is 1, 2, and 3, respectively. But I'm asking specifically the force of on Q4 as a result of Q1, in what direction is that force? It would be to the right because it's repulsive. And so if I draw a line connecting these charges, then the force has to lie along this left-right line. And since it's repulsive, it has to be pointing away. So I'm going to call this F1. And then the last one is I've got a vertical line here. And so that should tell me that the force on Q4 as a result of Q3 should either be down or it should be up. In which case, since they are repulsive, it's going up. And let's call this F3. Okay? So the magnitude of F1 is going to be equal to K times Q1 times Q4 over L squared. Right? KQ1 Q4 over L squared. Maggie? Yes, since we're talking about magnitude, that would be a good thing to go ahead and do. So let's just take the magnitude of this, so we're going to take the absolute value. In which case, this is going to be the 8.988 times 10 to the whatever. You've got this one is going to be the plus 3 nanocoulombs. You've got Q4 is plus 3 nanocoulombs over the 5 centimeters squared. And what does that give us in terms of our, well, let me write it down. What does this give us in terms of our force from the first charge acting on the fourth charge? 10 to the 9 times 3 times 10 to the minus 9 squared is what that would come out to be over 0.05 squared. Get 81. You'll have to use a calculator. I solved it a different way in my notes. 81 times 10 to the minus 9 divided by 1/20th squared, so times 400. I'm going to go with 32,000 times 10 to the minus 9. I'm going to go with 3.2 times 10 to the minus 4. Anybody? 3.2 times 10 to the minus 5. I was off by 1 order of magnitude. 3.2 times 10 to the minus 5 newtons. I used to do a game at Harding. I'll have to start doing it where I bring in a bowl of candy, and if you can beat me on a calculator faster than I can do mental math, then you get a piece of candy. Yes, right here.
Why did you convert the centimeters to?
Meters is the standard SI unit for distance, so you have to convert centimeters to meters if we want to deal with newtons. Okay, F3, it's going to turn out, we've got the same K, We've got the same two magnitudes of charges, 3 nanocoulombs apiece, and we've got the same distance even. So it turns out that the magnitude of F3 is also going to be 3.2 times 10 to the minus 5 newtons. But here's where things get a little bit more complicated, because now with F2, I still get K times Q2, Q4, all divided by now the distance between them squared, which is no longer L. The distance between the bottom left charge and the top right charge is not L. What? It's not L squared over 2. That's a good idea, though. If you look here, you've got each one of these sides, so it becomes, you got to do the Pythagorean theorem, and it comes out that if this is the distance r, r comes out to be the square root of 2L squared, or what's going to be more convenient to us, since we have to square r anyway, r squared is going to be equal to 2L squared. So I've got that this is K, Q2, Q4 over 2L squared. So everything else is the same except I'm dividing by 2. So that's 1.6 times 10 to the minus 5 newtons for each one of those 3 individual forces without any direction acting on it whatsoever. Okay? Sorry? It is a negative 5. Yes, sorry. It's negative. You should try talking to it sometimes. It's always bringing me down. Just like gravity, right? I'm telling you, this is just the start of the bad jokes.
John Mayer said it best.
I know who John Mayer is, but I don't know in what context.
You don't know Gravity by John Mayer?
No. You have to understand my pop culture. I'm a physicist. Maybe that should contextualize it, right? My knowledge of pop culture is incredibly thin. Just send it to me on Canvas or in an email. Send me the Spotify link. Okay, so now if we're asked to find the net force, or the force exerted by these point charges on the fourth charge, how do we resolve this into some sort of net charge? Net force, excuse me. Yes. He said it so well, and I know some of you who heard that are already downcast, and those of you who didn't hear it, we have to resolve these things into their vector components and then put vector components that are parallel to one another together and then bring it back together in one main package. Yes? They're the same because we're talking about a 45-degree angle right here, right? So if I look at this total angle here, because we always measure counterclockwise from the positive x-axis, so I've got from the x-axis to the y-axis is 90 degrees, from the y-axis to the negative x-axis is 90 degrees, and then I've got an additional 45 degrees because this is a square, so my net angle is 225 degrees, is one way that you could do this. And so if I want to know, for example, f sub x is going to be f1 and f2 have x components. So fx is f1, and implicitly this would be times the cosine of 0 degrees, plus f2 times the cosine of 225 degrees. And that comes out, once you work it out, to be 2.1 times 10 to the minus 5 newtons. And as was suggested, if you do the math for Fy, because this is at a 45-degree angle off of one of the axes, this would be F3 times the sine of 90 degrees, which is 1. Cosine of 0 is 1. Cosine of 90 is 1. Plus F2 times the sine of 225 degrees. That 2 comes out to be 2.1 times 10 to the minus 5 newtons. And so one way that you might be asked on Achieve to write this out is if it asked for it in IJK notation, then you would write this as F as a vector onto charge 4 is equal to 2.1 times 10 to the minus 5 newtons times I hat plus J hat. That would be the most condensed way that you could write that. Or sometimes on Achieve it asks you, okay, how would you write this as a vector magnitude with some direction? How would I figure that out? Well, remember, a vector magnitude, the net force on F is going to be the square root of its x component squared plus its y component squared. Or in this case, it's 2 times 2.1. Well, I guess just you can convince yourself that this is true, but it comes out that this is equal to 2.1 times 10 to the minus 5 newtons times the square root of 2, since they're the same. And that comes out to be 2.97 times 10 to the minus 5 newtons. How do I find in what direction this is pointing? Does anybody remember? Yes, up here, 6th, 7th row. Yeah, so if you want to know its angle off of the x-axis in the counterclockwise direction, you've got theta is equal to the arctangent, or we might say the tan inverse, of the y component over the x component. Well, that's the tan inverse, since they have the same magnitude in this problem, of 1, and the tan inverse of 1 is 45 degrees. No calculator needed. Get that out of here. Use your noggins. Any questions on this one? Wahoo! Okay, so, wait, say that again. So why are we taking the sine and cosine only on F2?
No, I understand that.
Okay.
Why is F4
Only the x and y components here?
Yes, why are you adding the other?
So his question was, why am I using F sub x and F sub y and not the charges from F1, 2, and 3, I think? Is that right? 1 and 3? Because they are wrapped up in here. Fx is a sum of F1 and the tiny components of F2. So I'm using Fx right here. And I'm using Fy, which is made up of F3 and F2. Because the cosine and sine of the arguments that I chose are 1, not 0. Yeah, implicitly, I left off on here that F sub x could have also had an additional term of F3 times the cosine of 90 degrees, in which case that's 0. And Fy also has F1 times the sine of 0 degrees, which that also is 0. So actually on Fx and Fy, I'm taking all three forces into account. It just so happened that just by geometrical observation, I knew that F3 had 0 component in X and F1 had 0 component in Y.
Can you explain a little better why you have to measure the angle from the x-axis? So, like, why is it?
Okay, Nate, let me answer this. Let me see what this question is too.
So how did you get I get that you have the degrees, but how did you choose that the Q1 to Q4 was where you start, I guess? Why did you start on
Okay, so two different questions. How did I know it was 45 or 225 degrees? And how did I know where to start, like which one to start with? Okay, so this is the easier question. I don't have to draw anything out. The net force is always going to be the sum of the forces that are tugging on this thing. So I could have found F1, F2, or F3 first. It didn't matter the order of F1, F2, F3. I just needed to find what their X and Y components were as the net force. So if you find that, then it doesn't matter what order you calculate the forces in. It just is easier for me to think about the ones that only have X components or Y components. That's why I did F1 and F3 first. But I could have found F2 first, any of them. Regarding the how did I know that this was 45 degrees here? So let's go up to this figure. In fact, I'm going to borrow a little bit from the ladder figure. And I'm going to draw an XY coordinate system, and this is going to look a little bit weird, but I'm going to draw an XY coordinate system centered on Q4 here, right? And so that means I've got to drop Q3 here, Q1 here, and then Q2 right here, right? So I know to go from here to here is 90 degrees, right? And then I know to go from here to here is 90 degrees. But how do I know that this angle right here, I just told you by inspection that it was 45 degrees? Does someone want to elucidate for us how I know that that's 45 degrees? Yeah, so packing apart both things that he said, because he talked about the trigonometric way and the geometrical way to understand it. I chose the geometrical way, and because of geometry, I know that this is a right angle, right? I mean, going from Q3 to Q4 to Q1 is a right angle, 90 degrees. And because this is a square, I know that this has to bisect that right angle, and half of 90 degrees is 45 degrees. If you didn't have that intuition, though, you could say, okay, well, this is side of length L, and this is side of length L. And if I want to know what this angle theta is right here, well, the tangent of theta is equal to its opposite side divided by its adjacent side, right? And then if I take the arctangent of that, it's the same as what I was doing before, the arctangent of 1, so 45 degrees. So now I know that theta equals 45 degrees, right? And the angles that we're using our sine and cosine conventions are the angle measured counterclockwise from the positive x-axis. So to get to this green line right here, I've got to have 90 degrees plus 90 degrees to go from here to here and then here to here plus 45 degrees. That comes out to be 225 degrees. And if I take the sine, cosine, and tangent of that, then I don't have to worry about whether my force is pointed in the positive or negative direction because, well, the sine and cosine of 225 degrees are both going to be negative.
So I guess
So if you were doing this on your own, this is a good question. In fact, you do have a homework problem just like this due like next Tuesday or Thursday. It's not going to be 45 degrees. And so the reason is your charges are not going to align in a nice square grid. I think the homework problem that I give you is you've got Q1 and then Q2 and Q3. It might not even be that nicely played anyway. It might be something like this, where you don't necessarily, like this is maybe 2, side of length 2, and this is side of length 5. So you always need to do the trig to figure out in what direction things are pointed. I mean, this first one is easy. If you're trying to find the force on this charge right here, I mean, you'd have an attractive force going down like that. I know that that is a vertical only force. The more difficult one would be this one right here. So how do I find maybe this angle theta, right? Well, again, I've got theta. The tangent to theta is the opposite, so 2, over the adjacent, which is 5. So I'd have to find the angle that way and figure out what it is. Okay? So always do the trig to rectify angles if you are unsure whatsoever.
Back in the original equation, f of x and f of y, is that like you're adding the starting and end? Like, what is f1 cosine 0 and f2 cosine 2?
Remember, when we're trying to find the x components of vectors or of any forces or any vector, right? I have to only figure out how much of that vector aligns to the x-axis. If you need a brush up on vector algebra, I can publish my Phys 1 lecture, but we'll have to move on because that was a Phys 1 thing. But you can come talk to me about it after class or during office hours. But if you need a brush up on vectors, I think I've actually posted some of that on Canvas already in like the student help module or something, but that will walk you through how to break vectors down into components and why we did all of that up there. Okay, let's move on. Done with that PowerPoint or slide deck. Ready for this one. I'll put here. So new slide deck, oh, no, wait, don't scan that QR code yet. I've got to reset the results from last semester. Reset results. Now you can scan the QR code, and we'll dive into new material. Ooh, 30 minutes left in class. I mean the whole package. But you've got the whole package of Star Trek, too, and it's kind of done the same thing that Star Wars has done, right? I'm talking about the whole package of Star Trek. I've got a later question later on in the semester that asks you to rank the original, or the 9 saga movies. And traditionally, the last 3 rank at the bottom. What won last time. Star Wars won last semester too. For those of you who are just tapping away on the thumbs up, great. For those of you who put the question mark, Star Wars is it's a movie about a young Jedi. Well, you got to explain what a Jedi is. Okay, never mind. Which one? Star Wars. I like Star Wars. It goes into my youth, further back for me. A quick note. I think I said I failed to say this the other day, but you have tutoring available to you. You can either schedule tutoring or you can do drop-in tutoring through the Student Success Center. Both take place in the library. I know that having 400 students in one semester, my time is very limited, and so it might be hard to catch me during office hours and get your question answered, but maybe, just maybe, that would be a good place to go. So now, We get to take this abstract action at a distance type force called the electric force, and we get to abstractify it even further. And we're going to discuss the idea of electric fields. So it says last time, my days fell a little bit different this semester, we saw that the Coulomb force is a non-contact force. That is, the charges need not be in touch with one another to experience the force. And what we're going to do is map this Coulomb force over the entire universe, and the map that is left behind we are going to call an electric field. So if you hear me saying the idea of a field, and you're like, a field is something that has a lot of grass in that you mow occasionally. A field is an abstract concept that we use in physics that will give us an idea as to how other things in the universe will respond to the thing creating the field. Okay? So if we bring other things into this universe and place them in the field tells us how the new thing is going to respond. That's all a field is. It's a map over the entire universe. Essentially, charged particles produce electric fields the electric fields in turn exert forces on other charged particles. If you've ever seen the rubber sheet analogy for general relativity, where you've got like the bowling ball in the center and the baseball spinning around it on the outside, what is being mapped by the rubber sheet is the gravitational field or the gravitational space-time field as predicted by general relativity. So if you've seen that, you're at least on the right track towards a framework for understanding the electric field. Okay? So electric fields. We're going to consider the net force here on Q0 in this figure to the right. Hopefully that's showing up all right. Yeah. We're going to consider the net force on Q0 that come from charges 1, 2, and 3, where each of the individual components of force are going to be represented by these smaller pinkish, purplish lines here. And then here's a big word for you, this periwinkle line here. The periwinkle line is going to be the net force. I only know that because my mother claims that that's her favorite color, periwinkle, that kind of off purple. So now that we know what the net force is here, the net force being this light purple line, if we divide that force by the charge that's experiencing the force, so take the force, divide by the charge experiencing the force, which in this case is Q0, what is left behind is the electric field at that point in space. So all we've done, I told you the electric field measures what the force is going to look like over the entire universe. We have successfully done it over a single point in space. Right? Only an infinite amount of space left to go. Woohoo! But you'll get a feel for what I'm talking about maybe in just a second, that if I move Q0 around and watch how the net force is going to respond, but then I'm always keeping in mind that I'm dividing by Q0, the charge experiencing the force, it's going to give me a map of the electric field. In fact, you can click on this link here. I'm going to show it, but if you want to save it for later, what we're going to get is, let's say it said we had a charge kind of right here. We had a charge kind of right here. And then we had a charge up here, right? I think it was something like that. Let me go back. Oh, no, it was a negative charge. We had a negative charge right here. And so what we did on this problem was we had a force that kind of looked something like this right here. I don't have it perfectly mapped out, but the dark red line is showing you the direction of the force and by extension, the direction of the electric field. And if I move this yellow line around, which is for us is going to represent Q0, you're going to see how the net force is going to respond as I move this out throughout the entirety of space. Right? The force, the net force, is always going to be pointed in the direction of the red line connected to the yellow dot. And by extension, the electric field is going to point in that direction as well. What the little white arrows on this simulation are showing you is if you can map that over the entirety of the universe, the white lines are what are called a vector field. It is showing you what the electric field is going to look like in the entirety of space, where the direction is easy to ascertain from the direction of the arrows, and then the opacity of the arrow determines its strength. Yes, Grayson. Periwinkle? Yeah. Yeah. So his question was, okay, if we go back to that figure, it's gotten small now, but if I go back to the figure, you'll notice that it is closer, it's closest to Q3. And so it's going to get a lot of left-leaning force here and very little right-leaning force due to Q1. And so the left overcomes what is here on the right. All three forces are up, so that tells us that we have a vector that's going to, a net vector that's going to be up, and since left is stronger than right, one that's going to be up and to the left. Good. And you can see that here specifically with wherever I dropped that charge. So if I dump it right here, we get the exact same thing, right? A force that's up and to the left. Yes. So his question was, is the repulsive force always 180 degrees away from the charge giving the force? Yes, because of what we said, Coulomb's law, right? It has to be along the line, connecting them. Well, this would be 0 degrees if it was attractive. And if I'm along that line, then it has to be 180 degrees. Yeah. Good. Okay. If you want to better understand electric fields, I strongly encourage you to spend 15 minutes just playing around with this thing tonight, tomorrow, before the next class.
So, would you define the electric field as like the set of all of the white arrows on that screen?
Yes. Not just on that screen, though. In the entire universe. Yes. The electric field is the set of all of the white arrows, their directions and magnitudes, over the entire universe. Good. Okay. So our standard SI unit of electric field strength is going to be the units of force, which is Newton, divided by the units of charge, which is Coulomb. So the standard SI unit, there's no derived unit. We just use newtons per Coulomb. All right. So when a 5 nanocoulomb test charge is placed at a certain point, it experiences a force of 2 times 10 to the minus 4, newtons drop down here, newtons in the positive x direction. What is the electric field at this point? And you can assume that the test charge is positive 5 nanocoulombs. I can press C to allow the responses. Okay, so the correct answer is the first one, the 40 kilonewtons per coulomb in positive x. For those of you who put the second answer the 40 kilonewtons per coulomb in negative x. Since we've got a force that is going, sorry, I've got to orient myself to the right, positive x, but I'm dividing by a positive test charge. I'm taking a positive number, dividing by a positive number, I still get a positive number. So to the right, it's in positive x, not in negative x. Good. Opposite question. What is the force on an electron placed at a point in space where the electric field is 4 times 10 to the 4 in the plus x direction? Bear in mind, an electron has a charge of 1.602 times 10 to the minus 19 coulombs, negative of that. The first one? We'll come back to that in a second. All right, good. Y'all are on the right track here for this one. Good. 6.4 femtonewtons in minus x. Good. The question was, how did you get the answer to, I'm assuming, each of those? Let's go to day 2 here. I'll scroll to the bottom of day 2. In the first one, you had Q is equal to plus 5 nanocoulombs. And I think I said that the force, I don't even remember, the force was equal to something. Here we go. The force is equal to 2 times 10 to the minus 4 newtons plus 2 times 10 to the minus 4 newtons in the I-hat direction. So if you want to know E is equal to F divided by Q by the definition of the electric field. So you've got plus 2 times 10 to the minus 4 I-hat divided by plus 5 times 10 to the minus 9. That gives you whatever the answer was for that one. And then I told you in the second question I just asked you what the electric field was, and I told you what Q was, and that's how you'd calculate F, where Q in this case would be minus the elementary charge, so minus 1.602 times 10 to the minus 19. It's in nanocoulombs. Nano is the SI prefix for 10 to the minus 9. Again, I would encourage you guys, if you are uncomfortable working with micro, nano, pico, and femto, I don't think we use atto at all this semester, but at least micro, nano, pico, and femto, you're going to want to be comfortable with those 4. All right, so in general, from Coulomb's law, we know that a force on a charge Q naught at a point P from another charge Q sub I, this is just a restatement of Coulomb's law, just with different variables from before. But what I'm trying to get you to see is that if we take, for example here, the force and divide it by Q naught, which by definition gives us the electric field at that point, well, all we have is essentially Coulomb's law, but just with one charge in the in the numerator instead of 2. So Coulomb's law was a constant times 2 charges divided by a distance squared. The electric field of a point charge, I should say this electric field's generalized. I would even further state that as electric fields of point charges generalized. The electric field is a constant times 1 charge divided by a distance squared. Questions on where we've gotten to so far? Yeah, it's r squared sub IP. And what that's saying is the distance squared from charge I at point P. I try to make this big enough to fit on the screen and make it easy for you to see. I will say, I can even turn down the lights. I'm sorry I didn't do that. But in addition, if you log in on your device, you should be able to scroll on your device and see on there too some of the benefit of using it this way. Don't worry about it. It's a different classroom setting than most of us are used to.
Q naught is at point P.
Yeah, Q naught is at point P, exactly. Field point P is where Q naught is. All right. Sorry I didn't turn on the lights sooner when we've got 13 minutes left in class. Something to note, although it's not explicitly stated before, it's worth noting that the electric field points away from positive source charges and toward negative source charges. Electric field lines point towards negative charges and away from positive charges. And again, this is where that PhET demonstration should come in handy, because the force and the electric field, the electric force and the electric field for a positive charge should be parallel, according to the equation relating those two. Why am I making a big deal about that? Well, if you go back to this PhET demonstration as I had it before, you could envision that if I have a positive charge existing out here in the universe, and these white lines represent the electric field pointing away from that positive charge, then if I drop this point here, and that being a positive charge, it's not inconceivable, in fact it is intuitive to think that that yellow dot, which represents a positive test charge, should be repelled, or meaning pointing away from the positive charge that exists already on the screen here. Whereas if instead that were a negative charge, a positive test charge would be attracted towards the negative source charge. And so we would get that the electric field lines, or the Coulomb force experienced by a positive test charge, is going to be attractive or towards the negative charge. So in general, you get away from positive charges and towards negative charges for the electric field. Okay, so in which region would you expect to find a point where the electric field is 0? And the answer is not none of these. It's in region 1, 2, or 3. All right, so 4/5 of you, 5/6 of you got the right answer. It is in region 3. But for the remaining confusion here, let's look at region 2. In region 2, if I look here, the electric field is going to point to the left, away from the positive charge on the right, and toward, so to the left, the negative charge on the left. Both the electric fields from one and towards the left and right charge are going to point to the left. So I can never add two vectors pointing in the same direction and get them to come to 0. So it can't be region 2. So the only valid choices then remain as region 1 and region 3. So why is it region 3 and not region 1? Grayson? Right, so Grayson said they want to go towards negative and away from positive, and you can see the net result in region 3 and region 1 are both going to give us two vectors pointed in the opposite direction. But if we're just taking direction into account, that still doesn't tell us why the field could be 0 in region 3 but not region 1. Yeah, the charge on the left has higher magnitude, which means that it's going to exert a stronger electric field than the charge on the right because its charge is higher. So I have to get further away from the higher magnitude charge here to counterbalance the weaker field exerted by the positive charge on the right. You could think of that, you can, again, this is why this PhET demonstration is so powerful. If you go in, I can drop the negative charge on the left and the positive charge on the right, but the negative charge on the left is twice as strong as the charge on the right. And so if I play around here, the electric field never goes to 0. It's always in the net right direction. And then if I come to this region, it's always to the left. But I can find a place here. Maybe I should bring this positive charge in a little bit closer to make it a little bit easier to find. I can find a place here where the electric field goes to 0, and you can't see on the screen, I'm sure, but if you pull this up on your own devices, there are vectors pointing to the left here and vectors pointing to the right. So at some point, this has to switch directions, meaning that the field is 0 somewhere right in here. Okay, let's talk about electric field lines, and then we will have to be done for today. Electric field lines are going to give us, per Bill's comment earlier, of the field as a map of all of the arrows over the entirety of the universe, is now if we connect the arrows and make them lines, that's where we come up with the idea of an electric field line. So a few rules. Choose a number of lines per charge. Let's say I'm going to choose 8 lines per nanocoulomb, or 4 lines per nanocoulomb of charge. Lines should radiate away from positive charges and terminate on negative charges, and the density of lines corresponds to the electric field strength. The first two, one is a choice, the second one is intuitive, the third one maybe not so intuitive as to what it's saying. Well, if you look here, the lines very close to this positive charge, they are very close together, meaning they have high density. Whereas as I get away from this positive test charge, the lines spread out, the density goes down. And so all this is saying is where the density of lines is high, I have higher electric field strength than where the density is low, further away, which is exactly what we saw when we said that the electric field of a point charge is kq over r squared, right? That the field gets weaker as you move away from the charge, which is exactly what this figure is showing here. So choose a number of lines per charge, radiate away from positive, terminate on negative, and density corresponds to strength. And so this is where you get an idea of, okay, well, what does this look like for two positive charges in the same region? Well, you get that the lines have to radiate away from one another, or from both charges. I get that the field is strongest right next to each of these charges, and it just so happens that no matter how many lines I draw, instead of choosing, let's see, they chose 2, 4, 6, I lost count. I can't count it. But let's say they chose 8 lines per charge. No matter if I'd chosen 16, if I'd chosen 32, 2 to the 100, however many lines I chose, the density would drop to 0. They would always be radiating from this point here, meaning that the electric field drops to 0 between these two positive charges that are equal in magnitude. And it just so happens it does so right in between them, at the midpoint. If the charge on the left was twice as strong as the charge on the right, there would be more lines coming out of the one on the left as there would be on the right. but they still wouldn't necessarily terminate on the positive charge. You just have more radiating out away from this positive charge. In fact, I think 2 slides from now, I have exactly what you're talking about. If I have a positive and negative, you get here what you might know colloquially from chemistry or something else. This would be a dipole. Because these are equal magnitude charges but opposite sign, for every line that I have here coming out of the positive charge, I have that line terminating on the negative charge. And you say, well, what about these that break out here? Well, it's just the sheer limitations of what I can show on the screen, but you can imagine it does go way out here above the figure and then come back down here. Same with this one. It's going to go above the screen and then come back in over here, but they are the same line that come in and out, sometimes even as far as infinity. And the last one that I have is per the last, Michael, right? Michael asked, right? What? Dalton. What Dalton suggested to us is these aren't the same sign, but what if one is twice its magnitude in charge? Then what would that look like? Well, it would look like something here. All right. Y'all have a great day. If you've got questions, I'm going to grab some lunch here before my office hours at 1. Otherwise, I will see you there.